Okay. Am I audible? Okay. Hello everyone. Here we are presenting our work related to balanced affinity loss function to detect highly imbalanced threats depicted within the X-ray scans. Here actually we address two of the major challenges which are faced in the aviation security. First is declutterness. Within the X-ray budget, it's very difficult to identify the items from the 2D scans because of the occlusion and the clutter that is depicted within it. And the other problem is that threatening items comes very rarely in the aviation screening. I mean, you don't expect to see threatening items every day. It's very rare in the real world. So in order to solve both of these problems, first of all, we developed an instant segmentation framework that does not leverage the RGB scan or the X-ray scan, rather it actually leverages the contours. So it highlights the contours of different items, and based upon those contours, we performed an instant segmentation using an auto-encoder network. And then we identify the threatening items based upon the bounding boxes that covers them. And the other thing which we addressed is the imbalanced nature of the threatening items. To handle this, we developed a balanced affinity loss function that minimizes the distance between the similar class clusters and maximizes the distance between interclass clusters. So both of the distribution of different classes are separated, and rather than minimizing and maximizing based upon the Euclidean distance, we developed a Gaussian infinity expression that actually computes the distance between both classes, both negative and positive classes, based upon the Gaussian distribution, which actually results in a better differentiation between clusters of different classes as compared to the conventional cross entropy loss function and the affinity loss function. And because of this, how we constrained the model, we achieved around up to 25.81% improvement as compared to the state-of-the-art framework in terms of mean intersection over union scores. Thank you so much. Thank you.
Okay, start. Okay. I am the first author and the presenter Juren Huang from National Taiwan University, and this work is for cloud removal from temporal information. Okay, you can see here, the satellite images are usually occluded by the cloud. So, these occluded satellite images cannot apply for downstream tasks, such as slane cover classification or environment monitoring. So, cloud removal is an important preprocessing before applying on the downstream tasks. Okay. The cloud can be simply divided into two different types, thick cloud and thin cloud. Okay. The thin cloud is similar to haze, and the thick cloud is shown here. Okay. The thin cloud the thin cloud can be solved by just a single satellite imagery, but there is not an effective way to the thick cloud occlusion. So in this work, we deal with both types of cloud occlusion phenomena by the temporal information from the satellite imagery. Okay, in this work, we collected the satellite imagery with and without the clouds and with and without cloud occlusion from the Sentinel-2 satellites, which is from Europe. An example is shown here. The top row shows the cloudy imagery, and the down row shows the corresponding cloud imagery. Okay, our motivation is that we use the temporal information to recover the corresponding cloud imagery. Since the temporal cloud images may have different visibility in the same region. So why don't we use this information to fill the cloudy region in the temporal information? Okay, so this is our model architecture. Our model architecture is, we refer to the previous work of setting. So we take the three inputs as inputs. We take the three satellite images as inputs. And these images will pass through a feature extractor to get a representation. Okay, this representation will concatenate with the neighbor to fit into an encoder for downsampling. Okay, this representation will fit into a conform module to conduct an attention mechanism to make the model find the most critical representation in the temporal information. Okay, this representation will pass through an encoder to generate the corresponding cloud imagery. Okay, the design of the feature extractor is shown below. Okay, we add an additional cloud detection module to detect the location of the cloud. This cloud mask will multiply back to the original extracted representation to downweight the cloudy region in the input image and increase the weight of the cloudy region in the images. Okay, the output of the feature extractor is an auxiliary image and feature maps and a cloud mask. Okay, this auxiliary image will compute the L1 loss to the corresponding cloud image. Okay, this feature map will pass through the encoder and decoder architecture to generate the corresponding cloud image. The cloud mask will compute the mean square error to the corresponding cloud mask to get the location of the clouds. Okay, in the experimental results, we evaluate our performance by using the PSNR and structure similarity. Okay, the higher of these two metrics, it means indicating that our model, our generating image is similar to the corresponding cloud image. So we use 3 different datasets to evaluate our performance. Formosa set 2, which is from Taiwan, and SEN2 and TC, and which is from Sentinel-2 satellites, which is from Europe, and STGAN dataset, which is from previous state-of-the-art paper. Okay. In these 3 datasets, our performance outperforms the previous work and achieves state-of-the-art performance. Okay. In the visualization results, we show that the 3 input cloud images and 3 corresponding generated cloud masks and the generated feed image from STGAN, and generated image from our model, and the corresponding cloud image. Okay, in the first column, you can see that the 3 cloud images are almost covered with the clouds. Our model can roughly generate the shape under the clouds. Okay, thanks for your attention.
Okay. Hi, I'm Daichi Horita from the University of Tokyo. Let me introduce our paper, translation of illustration artist style using Sailor Moon literal data. Okay? Yeah. So, in summary, we propose a novel image to image translation task, which called artist style translation. So, artist style translation aims to translate an original illustration to that of another artist style. So actually, in our paper, we define content images and style images. Content images is just using Sailor Moon. So Sailor Moon is the most famous animation in Japan. And style images is using other than Sailor Moon. We aim to generate output images using content and style. And content output images are expected to be like style images. So to achieve this novel task, we create dataset, which is Sailor Moon dataset.
Sailor Moon dataset, we focus on Sailor Moon literal movement. Sailor Moon literal movement is that illustrator all over the world draws a Sailor Moon with same contents, but using their style. So if we use this dataset, the generator can disentangle content and style easier. So yeah, let me introduce the detail of the Sailor Moon dataset. So this dataset consists of two sub-datasets. One is dataset S, and the other is dataset O. Dataset S means Sailor Moon, O means other than Sailor Moon. So actually, dataset S includes only Sailor Moon, but O includes other than Sailor Moon, such like kawaii illust. Yeah, so let me introduce our method. Our method is based on swapping autoencoder. Swapping autoencoder is a method to achieve image-to-image translation task with reference, I mean style images. So actually, the difference is just here. So I mean how to give a style images is different from original swapping autoencoder. Actually, we found that if we give more style images, such like 4 or 5 images, and the average of feature can improve the accuracy and quality. So we propose to use several style images. Let me introduce results. To conduct the experiments, we compare with swapping autoencoder and our method. Actually, swapping the result is shown here. From left to right, given images, given style images, and three are shown. The results, the output samples are shown here. So swapping autoencoder generate just using color features. So, but our method can achieve to generate output images correctly using style images. So, for example, this sorry, too small. These images has a big eye, but swapping autoencoder fails to generate big eye. But our method can achieve to generate with a big eye. So we can see that our method can achieve to generate more correctly. Yeah. So actually, to conduct a quantitative comparison, we train a classifier using dataset O. Dataset O has a label with authors. So I mean, class 1 is drawn by author A. Class 2 is drawn by author B. So then the classifier classify output images to class infer classes So I mean, classifier classifies which classes to be belonged. So actually, our method can achieve more high accuracy, and we found that using several samples, if we use more style images, we can improve the quality and quantitative scores. Yeah. So, and in conclusion, in this paper we propose a novel task, artist style translation. Yeah. So, and the task aims to generate output images with content images, which is only Sailor Moon, and style images, which are not Sailor Moon. Thank you. Okay?
Oh.
It's good. Okay, so hello, I'm Thibaut Durand from the Greek Laboratory Image team, and I'm going to introduce briefly my paper, Modular and Lightweight Networks for B-Scale Style Transfer. So it's about style transfer, but with two specificities. First, we use very lightweight networks, which are about 40,000 and 100,000 parameters. And the second specificity is that these networks are modular. It means that we use fine networks for transferring the fine textures of an image and coarse network for transferring the coarse structures of an image into a content image. And the fact is that we train those networks independently, but use them and combine them as we want during the evaluation. As you can see here, we combine a network trained for transferring those textures with a network trained for transferring those structures in this image. So it's a very light method for artistic style transfer, mixing styles at different scales. Thank you.
Should I stand here? Hello. So I am Professor Jayanto Mukhopadhyay from Indian Institute of Technology, Kharagpur, and I am presenting a work which with my students, Shai Phonikumar Maladi and also Anish Bhattacharya, who did the internship. It is on a video retargeting using the eye tracking information, and we have developed a novel algorithm for that. So the basic idea of video retargeting is that when online itself, when you are looking at a video, but suppose you are to transmit it, but you should transmit the relevant portions as the viewer is looking at the video. So suppose the viewer is with the eyeglass, where the eye tracker is there, and also there is a video camera, and that is what we are trying to do, so that you save bandwidth and also you have better resolution. So the processing pipeline in this case is that first we group the frames which are very similar, and initially we considered for that the density coefficients, because in the complex domain density coefficients could be better retrieved, and then after grouping the similar frames, so these are the similar frames that are we get these similar frames, but then further refinement is there because we are going down to the sub activity level. That means a video segment which considers a particular type of activities which focus of attention is a particular object. For that we required a surf feature, and in this way we have certain partitions. So we have a further partitioning of the sub activity level, and then we try to get the focus of attention, and there the eye tracking information, the saliency, gaze information is important. So we considered a mean gaze position, because from the eye tracker you get the gaze information where the viewers are looking, so mean gaze position, and we look at the deviations of mean gaze positions in subsequent frames, and then we take out those video chunks which are there are two types of chunks where there is a content and there is a transitions. So there is an algorithm by which we have found out this transition video chunk and video segment, and also the content video segment, and then using the eye gaze information we have defined the focus of attention, and then use the zooming and panning around that. We finally got the retargeted video with the larger objects. So that is what is the algorithm. Thank you. Was it okay?
Is it okay to start? Okay. So hi, I'm the author of this paper, Streaming Capable High Performance Architecture of Learned Image Compression Codecs. So basically what we did is we made a very high throughput and latency optimized architecture for the image compression, and you can see the results here are very outstanding. So for 720p images on RTX 2080 Ti, we can achieve more than 300 FPS encoding and 166 decoding. And even on this embedded platform, this is made by NVIDIA, an embedded board. And on this size image, which is the Kodak dataset size images, we can even achieve 88 FPS encoding and 35 FPS decoding. And this is based on the factorized prior model. So our implementations can achieve very high performance. And about the related work, the current implementations are not very efficient in throughput and latency because the past optimizations are more focused on the neural model and the entropy coder. Like the 1DN optimization, I think this is a Google paper, and there are like some faster neural model architectures presented in some other works. And there are also faster context models like the checkerboard, which is a last year paper, and channel-wise context model. And there are also works like high-performance entropy coders. But there's one missing part of this puzzle, which is there's no efficient integration of the neural model and the entropy coder as a system, because in most existing implementations, like the one made by compressed AI, which is very commonly used for evaluation purposes, the neural model runs on GPU and entropy coder runs on CPU. But for example, when the neural model runs, the CPU just sits there doing nothing, and the entropy coder runs, the GPU sits there doing nothing, and this is not very efficient. And if you check the resource usage, neither GPU or CPU reach 100%. So what we do is we present a efficient architecture for the image compression, and it works. The great things are it works with existing models. So here we use factorized prior as an example, and also the hyper prior you can see over there. And it can be combined with other optimizations as we show over there. So the method is actually very simple, and it's a very common approach, but it's very effective. So we apply the synchronous workloads via pipelining. So you can see here the green parts, like this GA, HA, these are neural models, and they are run on the GPU typically. And this is the quantization step and entropy coding. These are entropy coders. They are run on the CPU usually. And this dotted part belongs to the hyper prior model. And for example, in the factorized prior model, this is the main part, and the hyper prior adds this on top of it. And the decoder is very similar. You run the entropy coder one time on the CPU, and then dequantization and this synthesis transform on the GPU, and then CPU once again and GPU once again. And on the old architectures, this is not very efficient, so we propose this kind of pipelining. And when for example, this frame is processed first by the GPU, and then when it's getting processed by the CPU, the next frame just comes in and gets processed by the GPU. And so with this kind of pipelining, the bottleneck can be resolved and the resource usage can be maximized. And also there are some other optimizations, like we use Tensor RTS runtime instead of PyTorch, because this is highly efficient and it allows the models to be compiled into CUDA kernels, and also some low-level optimizations. And this optimization using Tensor RTS runtime enables us to use zero-copy memory and also memory pooling on embedded devices, because on this Xavier NX, the JetStem board, basically the CPU and GPU share the same memory, so there's no need to copy back and forth. So it allows us to use zero-copy memory. And you can see here the results are very, very good. The baseline is the one by compressed AI, and the B is our implementation without touching the neural model. So we just grab the factorized prior and the hyper prior model from the compressed AI, the pre-trained models, and we convert them into this implementation, and we just compare these two, and already boosts by about 3 times, and here about 4 times in FPS. And also now we changed the neural models a bit to introduce the 1DN optimization. The 1DN optimization replaces the GDN activation layer with a more efficient one, and here you can see the FPS can be a bit improved a bit further. And also the latency can be improved a bit as well, because it's benefited from this Tensor RTS runtime and zero-copy memory approach. However, this pipelining approach mostly benefits the FPS. And also on 720p images, you can see on the baseline implementation is almost unusable, but in our implementations, it can reach about 30 FPS and 37 with this 1DN. And also on hyperprior, it's about 33 as an encoder. So this basically represents how you would use an embedded device as like a security camera, and then you have a decoder that's like a centralized server on like surveillance systems. So we have also a demo here that represents this kind of encoding on embedded device and decoding on a centralized server case. If you like it, you can check out this URL. And finally, if we just port this implementation into a modern system like the 2080 Ti, we can reach very high performance, like here, more than 300 FPS of 720p videos encoding, and the decoding is also 166, and for hyperprior it's a bit less, 270, 280 and 157. And the latencies are also improved all over these platforms and image sizes. So that's basically our work. Thank you very much. Okay, thank you.
Okay, you can hear me? Okay. So this is my work, multi-scale gridded Gabor attention for cirrus segmentation. Essentially this problem was born out, we wanted to detect these, we wanted to study these really faint structures in galaxies. So if we have like two galaxies merging, there's lots of these interesting astronomical structures which appear, such as streams of gas which shoot out from the merger event. But there was a problem in studying these because we'd have these contaminating clouds which would obstruct our view of these. So we thought it would be a good idea to try and automatically detect where this contamination was using convolutional neural networks, so then astronomers could then avoid, say, heavily contaminated images. Doing this with just standard CNNs was very difficult just because the images were so large and we needed to study both the local textural patterns of the images alongside global context, which CNNs aren't really that great at doing. So we turned towards using attention to do so, but this is kind of actually more memory intensive than using just standard CNNs. So we set about kind of coming up with an efficient way to use self-attention to study the cirrus in these large images. The way that we did this was actually we take our image and we divide it into lots of small tiles on different scales. We calculate attention on each of the tiles and then stitch all of these attention maps back up together in kind of some hierarchical fashion, similar to, say, the way UNet works with its skip connections, where lower level features feed into higher level features. And so we obtain kind of this quite fine segmentation map at the end. The cirrus clouds also they exhibit these oriented structures inside them. In these images, when they're actually blown up, there's actually kind of a filamentary structure to the cirrus clouds. And these filaments tend to share a common orientation to them. So the streaks actually have kind of this, they share an orientation throughout the cloud. And we thought it would be helpful to the network if we could add some sort of orientation sensitivity. It would maybe help latch on to these oriented streaks in the cloud, and it would make it easier to tell apart cirrus clouds from high background in the image, for example. So the way that we did this was using Gabor filters, where we had multiple Gabor filters of different orientations. So kind of a set filter bank of Gabor filters, and we would then multiply or modify the underlying convolutional filter with all of these different Gabor filters, giving us, say, one convolutional filter turns into eight filters, which are dependent on different orientations. And roughly, this adds some sort of rotation robustness or invariance into the image, which is quite helpful for dealing with the different oriented streaks in our cirrus clouds. So with the Gabor kind of convolutions, we're able to add a dimension of different orientations into our convolutional layer. And using this extra orientation dimension, we then calculated attention over it. So you're able to calculate attention, say, spatial-wise, comparing different parts of the image or different channels of the features. And we chose to do this over different orientations, so we could compare, say, the feature activations of one orientation to another. And then finally, we also came up with a way to deal with uncertain annotations. Because the cirrus dust is so ambiguous to spot, there's a lot of disagreement in the annotations. Experts often disagreed with saying what was cirrus and what wasn't. So we came up with a loss function to actually train on ground truth, where it's not necessarily binary. There's actually kind of confidence values in between, where we divide each of these we divide confidence ranges into quartiles. So we have 4 different confidence ranges, and labels that are more confidently, where there's more annotator agreement, We would then boost these parts of the image so that they provide more feedback to the network. And so the network essentially learns more from, say, confident parts of the image than where there's uncertain annotations. We found that our network worked very well on this task where we want to use both global context and local textual understanding. There's a significant improvement on just standard CNNs. And then also we applied our network to a data set of natural images with just standard clouds, and which shared similar properties, same kind of ambiguous boundaries of clouds, and also the images were quite large, and we actually achieved state-of-the-art performance using our network. Yeah, I think that's everything. Yeah.
I'm almost wondering, you have these quartiles.
Yes.
Would essentially being having a we had.
Thank you. So there are people live there now? Cool. Cool. Well, hi everyone. That's over the internet. I guess I'm going to present my transformer compressed sensing via global image tokens. There's a couple novelties here. The ultimate goal, I guess, wasn't necessarily to beat state-of-the-art for compressed sensing, or at least in this case compressed sensing for MRI, but to just kind of show that there's a new token type. My expertise has been with MRI compressed sensing, so it was the application that I chose to demonstrate its performance. So the kaleidoscope transform is similar to something called the pixel unshuffle operator, which has been used since about 2016 for super resolution networks, at least primarily. We use that transform to generate tokens. So the idea is that you have one high resolution image. A twofold undersampling will create 4 copies of the original image. 4-fold undersampling creates 16 copies of the original image, and so on. So our idea was, can we use this transform to create smaller images that we can use as tokens for vision transformers? So quite commonly, image patches and axial tokens have been used for vision transformers. And so in the context of image denoising, again, we are now proposing this kaleidoscope or pixel shuffle token operator. Each of these tokens, I guess, inherently is going to be a bit more focused on certain aspects of the image. So one of those image scales is, for patches, for example, they're inherently limited to local image information. And within them, they're inherently limited to high frequency contexts. Axial, so columns and rows, again, inherently local. They only look at columns and they only look at rows, but they do contain low and high frequency information of the image. our kaleidoscope kaleidoscope tokens, sorry, inherently, because they're low resolution embeddings, have global information with only low frequency, I guess in this case, noise. So I'm not so sure how well it comes through in the camera, but with this image and this image, hopefully you can see with MRI compressed sensing, the artifacts kind of extend throughout the whole image, right? So this artifact, or this ringing artifact, it's structured from the very top all the way down to the very bottom. So you can imagine then, just using image patches, it can be very, very difficult to get rid of structured noise if it extends past the patch that you're trying to get rid of the noise on. So with these kaleidoscope tokens, you embed all of that noise into each one of the tokens, and your transformer can then get rid of the noise one low resolution image at a time, I guess. So kind of interestingly though, that does limit it to only low frequency noise, so it can be very difficult to get rid of high frequency components. In the results section over here, patches, the improvement from patch to kaleidoscope is only relatively small. So you can also see, particularly in RS6, the performance is about the same between patches and kaleidoscope tokens, but the real improvement was in combining these two token types. So the ensemble, which does an axial denoising step, a kaleidoscope denoising step, and then a patch denoising step, that performed best overall. It required the least amount of time, and it had the fewest number of parameters for the transformer neural network, just because each part of the step can specialize. So the axial tokens can specialize on a mixture of local information with low and high frequency components. The patches can specialize at high frequency local denoising, and the kaleidoscope tokens can specialize at low frequency global noise. So combining them, you end up with a slightly better a bit better performance than just doing one. And so yeah, I guess the proposal here is that you can use these tokens with image classification, object detection, really with anything that uses vision transformers. And then our team's currently working on a few extensions of on this transform of the kaleidoscope transform to try and reduce the total number of parameters in vision transformers as well. I think that's about it, I'm not sure. Cool. So is that all right?
I can go? Hi guys, my name is Rafael. I come from Portugal, from IT. And this is a work where we have applied convolutional neural networks and some handcrafted texture features in order to classify the severity stages in cases of collagen 6 related myopathy. So this is a progressive disease, a genetic disease, which causes loss of muscle tissue and a lot of problems in terms of posture, respiratory ability, and some cardiac problems as well. So the patients tend to die young, around 25 or 30 at most. And the follow-up for these diseases is mainly has to do with biopsies, so they spend a lot of time in hospitals. And we are trying to find an automated way to help physicians diagnose and have a follow-up outcome for that as well. So what we have done is that we have taken a segmentation from the quadriceps muscles from 26 patients. We have healthy patients, patients with mild symptoms and moderate to severe, and we are trying to classify those 3 stages. So we segment the muscles and then we put them through a convolutional neural network. That's what we have done first. So as you can see here, and we classify those learned features into 3 different classes. Then from a previous work that we had in ICIP last year, we also have a set of handcrafted texture features which are computed using a software called Mazda. And then we classify those features alone using only this fully convolutional network. And then we tried also to merge the 2 sets of features, both the learned features and the handcrafted texture features, into a single vector and classify that vector as a whole. So here you can see the confusion matrices. One thing that we are particularly happy about is that all the misclassifications occur between adjacent classes, so they're meaning that there are no healthy cases misclassified as severe cases and vice versa. This is important for the follow-up outcome of the patients, and also a very good result was obtained in identifying healthy patients, which would be important for meaning that the early detection is also possible using this. So currently what we are trying to improve a little bit is the mild case classification. Most of these cases got misclassified as moderate to severe because there might be, so this is a continuous scale and we are discretizing this. So one of the things that we could try in the future is using regression as the output of the network instead of discretizing as 3 classes, to provide another type of scale for the physicians. So that could be a next step. Also, we are thinking about including an automated segmentation, because these are all done by hand and this is extremely time consuming for the physicians, as they have to segment and annotate each muscle in the body from a whole body magnetic resonance scan individually. So they want a classification for each muscle individually, because the manifestations can be different across the body. And another thing that we are trying to do right now is using the attention maps, so providing the image as a whole without any kind of segmentation, only the annotations in each image, and then provide the physicians with the attention maps from the convolutional neural network, so that so that they can see at which points are more activated by each class. Okay, thank you.
So hi, what we did was we were trying to optimize the VVC for the field of video coding for machines. And for the traditional optimization for the human visual system, there is this concept called frequency-specific quantization, where you are quantizing the higher frequency components more coarsely in order to reduce the bitrate while not suffering any visual loss. So we try to transfer that principle to the task-driven image coding, so when a neural network is applied to the decoded image. And for that, we wanted to have an end-to-end trained transform coding framework, or that was in our training framework. And there we have our input image that is fed into the DCT. And then regularly you would usually quantize those DCT components. However, this is non-differentiable, so we had to substitute that quantization part with uniform noise. That's something that is done from the field of learned image compression. And then you can continue with your coding chain by applying the inverse DCT and applying the analysis network to the decoded image or to your noisy image representation then, and eventually obtaining the task loss. And then we have the two concurring goals here, feeding into the loss function of, on the one hand, the task loss. So we do not want to have the task loss increased here. But on the other hand, we want to have our scaling metrics here with which we can steer the noise. We want to have that increased such that eventually this results in a low bitrate. So in the end, we obtained those scaling matrices here, depending on our initial noise factor and also on our lambda, with which we can steer between the low task loss and a high scaling matrix. And when applying that into the VTM, into our test setup for the Cityscape data set, we can see here in the blue, we can see the standard VTM without any frequency-specific quantization, and those little dots here correspond to the different quantization matrices we applied. And there we can now see that we have coding gains except only one case compared to the standard VTM. And this results then, when we're just picking the optimal points for all quantization parameters, this results in 9% of bitrate gains. And also when comparing that to other human visual system optimized scaling matrices, we can obtain larger coding gains compared to the other metrics or compared to the other scaling lists of 4.4% and 4.2%, however sacrificing a little bit of coding gains for the regular coding gains of PSNR. So yeah, if you're interested in our work, those scaling lists are available here at GitHub, and yeah, thanks for listening. Thank you. So.
Okay.
That's fine. You can't rely on
Can I start now? So this is where to detect cancer in skin images. So in this case, the work is in two steps. One step is to detect interest region, the tumoral region inside the biopsy. In this case, we have histological images, and the pathology annotated the region where the tumor region is located. So the first step is to train a teacher and a student model. We have a few images with annotated with the annotation of the pathology, and a large database without annotation. So we use a teacher model with the label database to train a first model. After this model is used to predict the confidence in the large database. So we use the label database and the pseudo label of this non-annotated database to train a second model that is called student. So now we reconstruct the titles of the images, and we obtain the head maps of this is the prediction of this stage. So after we use the features of the titles, okay, to obtain a latent space of each biopsy. And the idea now is to use a contrastive learning to separate the latent space. So here, after use the proposed loss function, we obtain a latent space to separate the benign and malignant lesion. And in this case, we have this result for the first step, that it is the teacher and the student, and we can see that all the metrics are improving with the student paradigm. And after we use cross-entropy and the proposed loss function, and we can say that the results are better with the proposed method. And this is the result from another database that we use to test our methodology. So thank you so much for your attention.
Thank you.
Thank you.
I'll just
okay.
Leave it like that, and okay.
Vous allez me poser des questions ou Ah putain. Alors.
Tu le faire avec la personne qui était là tout à l'heure.
Bah oui là, mais au moins tu fais l'intéressé là. Bon. So my work is on this this new imaging technique, which is called dynamic full field optical coherence tomography, and it's supposed to help pathologists and overcome the very high acquisition time of gold standard histopathology, which is the principal way of doing tissue assessment for cancer detection or any kind of very thorough diagnosis at the cell level. So this technique, as I was telling you, is much faster, is maybe 5-10 minutes are required for a biopsy, as opposed to histopathology, which requires maybe 2 or 3 days. But the problem with this imaging is that it's not very known by doctors, so it's very hard to have a true diagnosis based on this. So this is where my work comes in, to do an automated diagnosis on these images, and to use actually the diagnosis produced by the pathologist on this gold standard imaging, for which we have a lot of information, and it's very robust, and it's been around for maybe tens of years. So coming back to the pipeline, we have the biopsy acquired with our imaging, and we have a global diagnosis acquired from the pathologists, and we are dealing with huge imaging with huge images. So we have to split them further into patches, and for this I have developed an algorithm based on the SLIC superpixel algorithm that I invite you to check out on GitHub, and which mimics the way a human looks at an image, and it splits it into further images, like smaller images. And from this group of tiles, we do a second selection, and we discard the patches bearing less information, and we keep the patches with the highest information, which are supposed to help the most for diagnosis. And those patches we feed in this multi-stream neural network, which takes all the patches at input and provides a local, an individual prediction for each patch. And the actual training is done by comparing the highest scoring patch, so the patch with the highest prediction, with the global prediction extracted from the pathologists. And with this, we managed to obtain a global prediction at the sample level, but also we have an idea of the diagnosis at the local level. Thank you. Putain, je bégaye là. Oula.
Leave it in and you're fine.
So in this work what we have done, that in the salmon fishing industry, the problem they happen is that when they farm the salmon fish, so what happened that there are certain viruses affect the salmon fish, and it is normally there is a one kind of virus called salmonid alpha virus, and that particular virus when it affects the salmon fish, they don't show any kind of behavioral changes or any kind of effect on their skin or anything. So at the third month, like after 12 weeks when salmons are so big, that time the infected fish hearts start bursting. So their heart has become so big that it cannot take the pressure of the blood flow, and so it bursts. And in that case, the salmon fishing industry has to discard the complete pool of the salmon fish. And as a result, this is a big economical loss for the fishing industry. And I come from this Norway, and in Norway the salmon fishing industry is quite a big contributor to the GDP of the Norway. So the aim of this particular work is that can we find that there is a functional change in the salmon fish heart due to this viral infection, and can we use AI to find it. So aim was that how quickly can we find the infection to the salmon fish. So what we did, we took this embryonic heart when the salmon fish is about to hatch from the egg. So that is called a day 0. That time we extracted the embryonic fish from it, and we extracted the salmon heart from it, and then that particular salmon embryonic heart we put into the petri dish, and we put a control and an uncontrolled. In uncontrolled we put the viral infection, and in control we kept as it is. And we then image at the day 0, at the day 7, at the day 14 and day 21. And for doing this, then we applied the AI, the ensemble technique for deep learning method, and we are able to detect the infection between the not infected and not infected by day 7. So now this was done with a very small pool of study. This was a pilot study with 10 samples, 5 in a control and 5 in an uncontrolled. And so this particular model might suffer from the overfitting of the problem, but then the challenge was that can we do with the small samples. So what we did, we took the video of it, simple video of it, and we converted into canny image, and then we did a morphological operation, and from that we extracted the contour of it, and then we applied the Butterworth filter to the sequence of image, and we got this time signal. And then for doing the ensemble, we applied 3 kind of Butterworth filter, and then so we got 3 kind of spectral graph. So from time signal we applied change into the Fourier domain, and we got the spectrogram, and that spectrogram is being applied to the deep model to train it. And then from fuzzy integral approach, Sugeno-Fuzzy integral approach, we did the ensemble of it, and then we found the classification between infected and uninfected heart. So now this pilot study has helped us to go for larger study. Now we have done a study with 200 fish samples, and now the result will be going to come in the future. Thank you. Is it okay?
Yes, that's fine. Thank you very much.
Where can I get to see this?
What?
Where can I get to see this?
From the YouTube channel of in your pockets?
Yeah.
That's fine.
Hello everyone. I'm presenting our work on style transfer using Wasserstein distance. So let me just briefly go through. I'm going to briefly go through this poster. So the image style transfer is the method of preserving the contents of the images. The first column is that, and apply the style of the style image, get the new output, and then these are the results. And then rightmost column we have our method, and then before that we have some examples from the existing ones. So let me talk about two representative works on image style transfer. First one is called Adain, and second one is called WCT. Adain uses the mean and variance of features on the image, so it's very fast, but it has low quality. For WCT, it does the whitening, so that the features are independent of each other, and then uses mean variance and covariance of the image features. Okay, so this is a brief summary of the existing algorithms. Adain is fast, but has a poorer quality. And WCT is slow, but better quality. And in our paper, we propose something called WCT opt, which is fast and still preserve fairly good result. So this is the main architecture of our proposed method. So we have the upper pass and lower pass. And then on the upper pass, we use image data from a COCO data set to use the encoder. And we have something called a small encoder or S encoder, which is about 25% size of the encoder. That is used for encoding the input image, and at the same time we use the same encoder and decoder, same encoder and same S encoder for the content style image. And we go through another pass at the bottom. So at the core of the algorithm, we use the Gaussian optimal transport. And then for optimality, we use Wasserstein distance. We use Gaussian features. And then after going through the decoder, we reconstruct the image. And then after that, we go through the encoder again to compute the perceptual loss from the upper pass. In the lower pass, we use the Adain and use the decoder, and then we get the output. Because we have the content and style image for the input, we can compute the content loss and style loss at the same time. So we have three different losses: perceptual loss, content loss, and style loss. They're linearly merged together to update the parameters of the encoder and small encoder. And the process is repeated until the training is over. After that, what we do is for inference time, is that you take the content and style image and go through the small encoder, use Adain, and get the resulting output. So by using this, it's faster. And by using this, we get better quality. So here are the results. The results can be best viewed if you look at the paper and then zoom in. So please do that. And then one thing I want to tell you that is that for flat areas, we do not have any artifacts like Adain or WCT where there are some styles aggressively applied to the content image. So we have a relatively similar content as the content image for the output. And at the same time, for detailed images, our method can preserve those details after applying the content style of the style images. If you go to the bottom, we have the runtime comparison. So basically, we have our algorithm works very fast for high resolution images compared with those existing ones, and our algorithm also at the same time gives very good results. So if you have more interest in, you can contact me there, or you can look into the paper and in the proceedings. And thank you so much for listening.
Okay, thank you very much.
Yeah. Was the audio okay with the mask? Oh, with the light. Okay.
leave it in your pocket. Okay, that's fine.
Okay, I'd like to explain our research in a nutshell, about 1 minute. The aims of our research is to removing shadows from document images, and in our research, shadow removal of document images using deep neural network is trained on only fully synthetic dataset, which I proposed rendered by Blender. So these datasets are created from scratch, so we can easily obtain ground truth images, shadow images, and shadow masks and foreground masks. And so we have proposed a network that can utilize these masks as a teacher signal for multitask learning. So, and our network achieves better results compared to other network. And also we found that the networks only trained on the proposed dataset, which is fully synthetic dataset, can perform well on real dataset, only trained on synthetic images and tested on real images. It performs well. That's it. Thank you.
We're fine.
Thank you.
Thank you.
So I'm to take it. Yeah. Let me just
Okay, fine. Donc, comme on n'a pas cet aspect raffinement dont je parlais, on a des réflexes un peu en dessous.
Right here, maybe.
Par contre, l'état de l'air, il a d'autres parties.
Okay.
And it slips right here.
Okay. So now everybody can listen to me. Yeah? Is it okay? So hello everyone. I'm going to present you my work about a fully learnable Gaussian derivative convolutional layer. The main idea of this work is that instead of using a table of parameters as a filter for my convolutional layer, we propose to use a more parametric form. And what we propose is to use a linear combination of Gaussian derivative filters which are transformed. The transformation of the following one: a scaling, a rotation, and a shift. But the parameters of this transformation are directly included in the expression of the Gaussian derivatives. And everything is included in a differentiable manner, so the network can learn the transformation parameters during the training process. It also learns the weight of the linear combination, and this approach allows to have the size of the filters, which is independent of the number of trainable parameters. I can use a 9x9 filter or a 3x3 filters. I still have the same number of trainable parameters. And so we applied it to two tasks. A classification one, we showed that we had competitive results with other closed approaches. And we also did a segmentation task where we used a classical unit and a unit using our proposed layer. And we obtained comparable performances, but we only used a quarter of trainable parameters. There is one drawback of this method, is that every time the parameters of the transformations are updated, it has to compute again. So during the training process, it's a little bit longer. Oh. Thank you very much.
C'est comme moi j'ai une livre actuellement, c'est la présence.
This right in your pocket and you're good to go.
Is the live broadcast already on? So what is it that I'm just going to talk about the paper, right? Okay, okay. Sure, of course. It's gone. Hello everybody. My name is Hongjie Yu from Huawei Munich Research Center. I'm also affiliated with Technical University of Munich. Today I'm presenting the work of CNN-based local tone mapping in the perceptual quantization domain, and this work is being presented at ICIP 2022. So the big motivation behind the work is that we have normally the high dynamic range images that range well above 4,000 nits. And those 4,000 nits cannot be properly reproduced by the commercial, let's say, displays that we currently have because they are restricted by the display technology. For example, you take your normal phone, they could display up to 500 nits, or the flagship phones, mobile phones, they display up to 1,000 nits. So we still need to compress the dynamic range, and people call this kind of dynamic range compression tone mapping. In our work, we decided to use the CNN neural network-based compression for the dynamic range. So as you can see here, the baseline that we took is the HDRNet proposed by researchers. And then what we do is that we modify the neural network, make it smaller, and instead of working directly on RGB channels, we work on the luminance channel. If you take a look at the pipeline algorithm here, please. The input what we have is the HDR PQ images. So the HDR PQ images are in RGB domain, the data set that we collected, and then convert to PQ, lumen. And then we extract the luminance from the RGB images using a standard conversion matrix. The luminance information goes through a guider filter. This is a typical edge preserving filter. By filtering, we could yield a detail layer. This is the edges that's being preserved by the filter, and also a base layer, which contains the low frequency information on the luminance, so the illumination. What we try to do is that use the modified HDRNet network to compress the dynamic range, and then using the compressed dynamic range composed with the detail layer, we could have a matrix. So this is for computing a gain compared to the original image. By computing the gain, you could have the, let's say, scaling factor. The scaling factor will then be multiplied in the linear domain with the original HDR image, and then you could clip it at your desired peak luminance. Let it be, for example, you have a phone that displays 1,000 nits, and then that luminance will be 1,000 nits. If you have HDR TV, even though people call it HDR, you still clip it at 500 nits, depending on the display capability. In the end, what you produce here is a tone-mapped ADR, where you have the dynamic range already compressed, and we try to do this to keep minimal color shift. So during our pipeline, you can already see we're compressing the HDR PQ RGB to LDR PQ RGB. And then here is the algorithm that we try to use to create the ground truth. Of course, you can take a look at the subjective evaluation here. This is very straightforward. Our goal is that we want to produce results as close to the ground truth as possible with very minimal oversaturation. As you can see from the baseline here, it's highlighted here. You don't see lots of detail in the lamps because they suffer from the oversaturation. For example, this is, if you normalize it to 0 to 1, you have a pixel of 1 and the neighborhood, they're all 1s. You don't see those details. We are trying to reproduce those details. And also another work that we brought to comparison, we only compare to the neural network-based method. Here you can see that they have a huge color shift. So our method's better. It's best in this case. It's also closer to the ground truth. We have a minimal oversaturation and color shift, and it's a better reproduction of highlights, details. And also here, you could take a look. Here is the objective evaluation. In order to compare to the ground truth, we take the traditional metric, objective metric for images. This is PSNR, peak signal to noise ratio. And those two, SSIM and MSSSIM, they are taken for comparing the structural similarity. As you can see from the table and also from the charts, that our method outperformed the baseline method, also the other comparative method, by, let's say, PSNR approximately on the average of 8 dB, improvement SSIM, MSSSIM, roughly 0.0044 and also 0.002 respectively. For the complexity, because we were able to compress the image instead of on RGB channels, 3 channels, we compress it on the luminance channel. On the neural network itself, we reduce the complexity. It's only left with 1/4 number of parameters of the original HDRNet in our comparison pipeline. And the inference speed, of course, you're reducing the network size, you're increasing the inference speed. So during inference, it's 1.5 times higher, it's 1.5 times faster than the baseline model. We not only tested on the RTX Titan, also tested on 1080p Ti. You are able to run it on 4K images as well. So to conclude this paper, what we propose here is a local TMNet. It is a CNN-based tone mapping operator. It's working fully on the perceptual quantization domain, which outperforms the baseline in comparing with the gain of 8 dB in PSNR on average, also in the gain in SSIM and MSSSIM. Our local tone mapping is done via the image layer decomposition. And the decomposition, we have the base layer, and then by the compression of base layer luminance, this scheme will help to reduce the network size and also the inference time, while providing better visual results to compare to the baseline in our experiment. We would like to invite you to please check out our work in the proceeding of ICIP 2022, and also check out our work on the website. And thank you very much. Is it good?
Yeah, thank you very much.
Thank you. Merci. Julien?
Yes.
By the way, we also presented something.
We are.
Okay, you're just.
We are.
slip it in your pocket.
Okay. Right, everything good. So, hello. My work is about conditional coding. So the motivation for conditional coding is very general. So when you have in an intercoding chain, you typically have a residual coding scheme. So you subtract the prediction frame from the to be coded frame, and then transmit this residual. However, this is just a very it's just a special case of the more general question of how to transmit a frame when we know the prediction signal. So there's been some previous work in literature, and one of the drawbacks of this work is the high complexity, because it uses an additional encoder here, which has to be run at decoding time. So to circumvent this problem, we now propose two new operators, generalized difference and generalized sum, which aim to replace this difference and sum in the traditional residual coding scheme. However, in preliminary experiments, we found that we should be able to switch between a traditional residual coding and the generalized difference coding. So we do this by combining them both in one network. So we jointly compress the generalized difference and the normal residual. So we can see here, if you just look at the blue parts of this encoder scheme, this is the overall structure. Just the blue parts are a normal residual coder, just the red parts are a generalized coder. In our experiments, we looked at different coding schemes with all the same backbone autoencoder, which is just a standard 4-layer autoencoder with hyperparameter and context model, which we do not change at all in our experiments, except for changing the first input layer for the needed number of channels. So we use off-the-shelf components surrounding it for motion estimation and compensation and transmission, but keep them fixed during training, so all the networks have the same input and output to have a very fair comparison. So when we look at the results, we can see that our network performs best of all the competitors. And when we go to the hybridization, so we have actually used this switch here, then we can see that we even gain a little bit more rate savings. In terms of complexity, you can also see that our method has very low complexity. We have here complexity in terms of number of network parameters, so we have only 6.7% additional complexity, which is very reasonable and still get very nice gains. So in conclusion, we can see that conditional coding offers large flexibility and it should be better than residual coding, but often comes with a higher complexity. And with our proposed extended generalized difference coder, XGDC, we are able to solve this problem, achieve low complexity, good hybridization, and good gains. Thank you very much.
Thank you very much. I will take it out.
Thank you.
Welcome.
And slip it in your back pocket.
Okay.
That's fine.
Okay, let me start. Okay. Hello, I'm Meguro Yamazaki from Computing Laboratory of Fujitsu. This is our work, deep feature compression using rate distortion optimization guided autoencoder. Okay. First, recently collaborative intelligence was proposed to efficiently utilize computational resources on edge device. To achieve this goal in collaborative intelligence, the DNN model is divided into two parts and deployed both edge device and the cloud, respectively. And the edge device collects the input image with some camera and executes the first part of the DNN model, and then transmits a feature map.
feature map is an intermediate layer out of the DNA. And then cloud receives the feature map and executes the second part of the DNA model to get prediction result. However, collaborative intelligence might increase the transmission data size because the data size of this feature map is quite large. To solve this problem, feature compression methods have been proposed. Feature compression method compresses the feature map at each device and then transmits the compressed feature map to the cloud, and the cloud restores the feature map. Okay? And there are some feature compression methods. Compressed feature map is not small enough. I show the data size of these 4 materials in this figure. Okay? The largest is a raw feature map, and the second is a raw image, and the third is a compressed feature map, and the last is a compressed image. So compressed feature map is smaller than raw feature map and raw image, but it is still larger than compressed image. So our goal is to reduce the data size of compressed feature map and make it smaller than compressed image. Okay? To achieve this goal, we take 2 approaches. First one is we utilize autoencoder to compress the feature map. Recently, autoencoder achieves very good compression performance in the image compression. And we expect to achieve good compression performance with this autoencoder in the feature compression. And we also utilize prediction error and the data size as a loss matrix to train the autoencoder. Previously, the autoencoder is trained with MSE or SSIM based loss function in the image compression. And the existing feature compression method also utilize MSE or SSIM. However, in the feature compression, restoring feature map exactly is not needed because restored feature map is only used for the DNA inference, and people don't see the restored feature map. Okay? Also, we train the autoencoder to keep prediction accuracy and to reduce the data size. Okay? Next, this is our proposal method architecture. The autoencoder is inserted between edge model and the cloud model. And the loss function is like this. The loss is sum of D and BPP. D is a loss function that represents a prediction error. And we carefully pick up this function according to the target model to which our proposal method is applied. And when training the autoencoder, both uncompressed prediction result Y and compressed prediction result Y hat are obtained, and then the loss is calculated with Y and Y hat and BPP. BPP is calculated with entropy model. After that, only the encoder and decoder weights are updated. Okay, and next, this is our proposal method, our autoencoder structure. Our autoencoder is based on Balay's autoencoder, and encoder consists of convolution and GDN layer, and decoder consists of deconvolution and inverse GDN layer. Okay, and this is our evaluation setup. Target model is BGG16 and resident 50 and Euro V3. And in the classification models, D is a cross entropy, and in Euro V3, D is a Euro loss function, which is proposed in Euro paper. And we have some partitioning point in the target model to verify our proposal method performance across target model. And BGG16 is partitioned after each max pooling layer, and resonant 50 is partitioned after each comb block, which is specified in resonant paper. And Euro V3 is partitioned after first 3 convolution layers, whose stride is 2. And the comparison method is HEBC and BBC. Both methods compresses a raw input image, and there are 2 metrics. First one is delta. Delta is difference between F1 scores in image classification model. And the image object detection model data is a difference between MAPs. And matrix 2 is data size after compression. And these are our results. Horizontal axis represents data size, and vertical axis represents delta. So lower left lower result is better. Okay. And this dashed line is HEBC and B present 50. However, in your B3, our proposed method only outperforms at 0.3, this gray line. This is because object detection model has to detect out of object and also predict size and position of object. So our proposal method have to keep out of feature and struggle to reduce data size. Okay, that's all from me. Thank you for listening. Okay.
Thank you very much.
Okay.
It's great. It's your back pocket. Okay.